In this video, we're going to address our main application of Chapter 2, and that is solving systems of ordinary differential equations. And we're going to do that using this diagonalization procedure that we've been developing in the last several videos. So we can talk about initial value problems, boundary value problems. Both of these can be addressed using this technique. We're going to focus our attention on initial value problems just so that the independent variable is always time, but the procedure can be applied equally as well to boundary value problems. So if you think back to your very first differential equations class, you would have solved the simplest differential equation you can imagine, which is a first order linear ODE, something like du dt is equal to a constant a times u. And you learn how to solve that using separation of variables. You bring all the u stuff, the dependent variable, to one side, all the t stuff, the independent variable, to the other side. You integrate both sides and you solve for u, and you get that you have an integration constant c times the exponential e to the at, where a is that constant right here. What we want to address is a much more complicated system, but it's based on the same ideas. So now we're going to look at a system of capital N coupled first order linear ordinary differential equations. So now we have capital N variables, u1, u2 through un, and we have capital N ordinary differential equations that involve all of those variables. So in our first equation, we have u1 dot, which is just du1 dt, and that's equal to a coefficient, say a11, times u1 plus a coefficient times u2 plus a coefficient times u3, all the way down the line to coefficient times un. And we'll also allow for the possibility of having forcing terms like f1 of t. Then for u2, du2 dt is equal to, again, a constant times u1 plus a constant times u2, and so on. And we have n of these equations. So we have capital N fully coupled linear ordinary differential equations for our n dependent variables u1 through un. And we need to solve them all together because the equations are coupled. I can't just solve one equation for u1, one equation for u2. All the equations involve all the variables in general, so I need to solve them in a coupled fashion. If it so happens that all these f's are 0, then we say the system is homogeneous. Again, homogeneous system just means that the system is equal to 0. So let's write that in matrix form. So we have u dot is equal to au plus f. U dot, that's du dt. U is the vector of all the dependent variables, u1 through un. F is the vector of all those forcing functions, f1 of t, f2 of t, through fn of t. And then this coefficient matrix is an n by n matrix. And because of the way we've defined these coefficients, we can collect them together conveniently in the form of a matrix using our usual notation. So we're going to start with the u variables, and with respect to which the problem is very complicated, fully coupled. We're going to uncouple through diagonalization in terms of a new set of variables v, solve the system in terms of v, which will be very straightforward because all the equations will be uncoupled, and then convert the system back to the original variables, the u's. So the way we do that is through this diagonalization. So that's going to be based on this transformation. So this is our original variable, u, so that's u1, u2 through un. Our new variables would be v, the vector v, v1 through vn, and the transformation matrix is going to be this modal matrix u, which, as before, will be comprised of the eigenvectors of A as its columns. So let's show that that does indeed diagonalize our system of ordinary differential equations. So we had u is equal to capital U v. Okay, that's our transformation. If I differentiate that, the elements of u are constants, so that would be u dot is equal to capital U times v dot. And so we can substitute that in to our system of equations, which was u dot is equal to au plus f. And so now the u dot is capital U times v dot from here. We had a times little u. Little u is big U times v, so this is a times u times v plus our f. Well, I'd like to write this as a system of first-order ODEs like we had in terms of U. So to do so, let me bring this U from the left to the right. To do that, we pre-multiply by the inverse of U. In doing so, I'll have U inverse times U, which is just the identity matrix I. So that leaves me with V dot. And then on the right-hand side, look what I have. I have U inverse times A times U times V, and then plus U inverse times F. Don't forget about this U inverse here times the F. The point now is look at our coefficient matrix in our new system of linear ordinary differential equations in terms of V. It's U inverse times A times U. As long as the eigenvectors are linearly independent, so 3 of those 4 cases, this will be a diagonal matrix D, in which case, as we'll see, the new system in terms of the variable V will be fully uncoupled. We can solve it as we did in the first class of differential equations. So here it is. Let's look at the case where F is 0, so homogeneous just to keep things simple for now. So writing it out in matrix form, we have our V1 dot, V2 dot through Vn dot. So that's our V vector dot, so dv dt. Here is our D matrix. That's U inverse times A times U, which is now a diagonal matrix with the eigenvalues on the diagonal, times V. So the first equation is V1 dot is equal to lambda 1 times V1 plus 0 times V2 plus 0 times V3 all the way to Vn. So that first equation is just V1 dot is equal to lambda 1 V1. The second equation is V2 dot is equal to 0 times V1 plus lambda 2 times V2, and then all the other terms vanish because of these zeros. So V2 dot is lambda 2 times V2, and that continues all the way to the last equation. So as you can see now, we have an uncoupled system of equations. I can solve this equation for V1, this equation for V2, all the way through to this equation for Vn, just as we did in that first class of differential equations. The solutions then look like these. So our C's are the integration constants, C1, C2 through Cn. The exponentials have our eigenvalues, lambda 1, lambda 2 through lambda n in them, and we know these uncoupled solutions. Now just like in all of these diagonalization applications, I know this result as soon as I have the eigenvalues. I don't actually have to do the U inverse times A times U. I know what the result is. It's an uncoupled system of equations. I know what the solutions are. Here they are. So I don't have to go through all those steps. I can immediately write this down. And then the V then, as a vector, is the C1e to the lambda 1t, C2e to the lambda 2t, and so forth to the nth term. So we took our hard problem, fully coupled system of capital N linear ODEs, converted it to a much easier system, fully uncoupled, solved it, which is very straightforward, and now we need to convert that back from the V variable back to the original U variable. So to do that, I have my solution for V now, that's right here. I pre-multiply the modal matrix U, and I get the solution in terms of the original dependent variables U1 through Un, and then we're done. If I have initial conditions, then I can get my C coefficients, the constants of integration as well. So some remarks about this process. For it to work, in other words, for it to fully uncouple the system of equations, I need to have a full complement of linearly independent regular eigenvectors. So that it works for A as symmetric and A is non-symmetric with distinct eigenvalues. Again, it's this fourth case non-symmetric A with repeated eigenvalues that I need to be careful of. Okay, the second point here is just saying that whereas we don't actually have to multiply out this U inverse times A times U, we do actually need U. We do need the modal matrix because I need that to multiply times V to get back to the U, to do that last step to convert it back to the original variable. So I do need the eigenvalues and the eigenvectors for those purposes. Now again, the Jordan canonical form, if I'm trying to solve a system of equations, and if the coefficient matrix happens to be non-symmetric and happens to have repeated eigenvalues, I expect to get a Jordan canonical matrix, Jordan canonical form. However, I can still solve it. It's not fully uncoupled, but I can still solve it using back substitution. So that last equation will be uncoupled. The next to last equation may be or maybe not, but I only have at most one unknown, maybe none. And so I can solve that using back substitution. So we can still solve them in that fourth case. We just have a little bit more work to do because it's not fully diagonalized. Now if I have a non-homogeneous system, so if the f's are non-zero, then this will be dealt with just like we did for a single differential equation. We'll get the homogeneous or complementary solution, we'll get the particular solution, and then we'll superimpose them together. Now this last point is actually kind of interesting. You'll notice that there's no requirement that A be non-singular for diagonalization. So when we're solving differential equations, we never actually ask the question, is our coefficient matrix singular or not? It never enters into our consideration when we're solving these systems of coupled linear ordinary differential equations using diagonalization. This last point I'm not going to go over in detail, but there is an alternative way to express this whole process for solving these systems of equations in vector matrix form. It more explicitly illustrates the eigenproblem. It's all mathematically equivalent to what we've just done, but it is an alternative approach that you can take a look at, and if you prefer, that of course is fine. So what we're going to do in the next several videos, we're going to go through a series of examples. Each example will have a new piece, something new that we're trying to illustrate. The first one will just be a simple 3x3 homogeneous system. We'll do that in the next video. We'll do a non-homogeneous system. And again, each example that we do will have some new piece of information or some new situation that we need to be able to deal with that's illustrated in that example.